there. So I'm going to talk about fitting and interpreting models today. So let's start with models that have numerical explanatory variables. All right, so remember our Paris painting data with its 3,000 plus observations and 60 plus variables? Well, we're going to import that today, and you'll notice that in the text, I've kind of compressed the importation process just so we can get along faster. Key things to point out is that when I'm reading in the CSV data, I've given it the option for multiple ways to indicate NA, including N/A, an empty space, as well as big nah. You can kind of compress our code down pretty tightly into a line. I recommend this from a quality of life standpoint, that you break it down so that it's logical and human readable, so that future you thanks you. Okay, so our goal with this data was last time we kind of crawled into trying to understand the relationship between height and width, and we noted that there seemed to be some effect for the type of painting. But let's kind of back up a little and then go in. So our goal is to predict height from width. And here's our plot. Our best fitting line seems to be this purple one, if all we're trying to do is explain height as a function of width. So I'm going to introduce tidy models here. They are brand new, straight off the presses, and they're a little controversial. But the idea is that you're given kind of a whole universe of tidiness, so you could in theory just stay in the tidyverse forever and never have to leave. It's a pretty nice framework, I think, although it is with controversy. But anyway, the idea is that, I already said this, so it's a tidy unified interface for fitting models. It converts statistical output into friendly formats, does some data splitting and resampling for you, and just provides a tidy statistical interface for both your data pre-processing and for your analysis. All right, so first we specify our model. And in tidy language, that's linear. We're going to use linear regression. And so we literally just tell it linear underscore regression, step 1. Step 2 is we pipe in the engine. Their language, not mine. And what we're doing is we're setting our model to estimate our regression using linear regression. There are other modeling types, but here's the basic approach. Step 3 is use formula syntax. So we've piped in all the pieces, but we have to ask it to fit the relationship that we're interested in. And so here we specify fit as a predicting height as a function of width. And we pipe in our data. Or we actually don't, we tell it where our data is. So this model object does all of those things. Effectively, what it does is it summons LM stats and pops their formula in. Eventually, tidyverse is probably going to tidy this up. But for now, it's still young and new. But what it does give us is our intercept and our width in inches. So let's take a little closer look at the model output. So, which I technically just did. It also gives us the fit time, which is nice. But let's move our key pieces from our output and plop them into our model. So we have estimated height starts with an average level. So if we have a width of 0, we expect our height to be 3 and a smidge, or 3.6. And then for every 1 unit increase in width, we predict a 0.78 unit increase in height. So yeah. Now we can tidy this all up, and what it does is it provides us with a tibble of our p-value, our fit statistic, and our estimate, as well as our standard error. It it gives us most of the key pieces. It doesn't give us all the pieces, but it gives us those that the tidyverse have considered essential. Personally, I think they should include more things. But I'm not on the tidyverse development team. So here, let's go through. So our slope is essentially reiterating what I already said. So the slope for each additional inch of painting width, the height is also expected to be higher. Now it's not that an increase in width will cause an increase in height, we're just describing the data that we have. But it's the same formula we would use to make a prediction. Now our intercept is here. So a painting that is 0 inches wide is expected to be 3.6 inches high on average. Now, does this estimate make any sense? No, because what painting is 0 wide? None. But this is kind of the mixed bag that you get with the intercept. Essentially, the intercept is telling us what our average is given everything else in our model is 0. I tend to mean or median center my data so that the intercept is more informative. And then in that case, the intercept tells us what the average height is in our data set, because setting width to 0 in that case is just the mean or median, depending on how I sliced it. And so it gives you a better sense of where the critical mass is, I think, from an intuitive standpoint. Now, I'm going to emphasize this here because while you all have been trained very well and know this, it's good to remind ourselves. So that just because we have a model that has a really nice correlation and has a beautiful R squared, allegedly, that doesn't mean it's causal. As this lovely XKCD comic kind of highlights. So when you interpret them, don't phrase it as don't put causal language in there. Be descriptive. It's safer. I mean, you can if it works in that context, but just from the coefficients alone, that doesn't give you any causal inference. Your data is where the causal inference comes in. Okay, so parameter estimation. Just so that we have it all, I know I'm covering stuff that you've covered in other classes, but I'm going to repeat it anyway. So we're interested in the beta value. So that's the population parameter. And here our model has 2 population parameters. One is for the intercept, or 0 is for the intercept, and 1 is for the population parameter of the slope in our model. But unfortunately, we don't actually know the population. And frankly, if we did, we wouldn't be needing to run this model. So we have to make estimates to do them. And that's why we've gone from Greek letters to Roman letters. And in this kind of model, the regression line minimizes the sum of squared residuals. There are different methods to estimate our best fitting line, but the regression line is probably the most, an ordinary least squared regression is probably the most straightforward. I have some notes on other types like MAD, which is my favorite name. But effectively what this is that if we set error to be the discrepancy between our observed and estimated y, then we find the estimated line that minimizes the sum of those squared discrepancies. So let me illustrate. Okay, here are our residuals. Let's throw the line in there. So here I lied. So we have the raw data, and now I've tossed in a least squared line. Now, the difference between our line and our points, that's the residual. My bad for misspeaking. And so those discrepancies are accounted for in this line, and what it does is it minimizes that distance, the square distance. All right, so some basic properties. So the regression line goes through the center of mass point. So that's the coordinates that correspond to the average x and the average y. So we can kind of restructure this data so that beta 0 is mean of y minus beta 1 of x, which is kind of cool. So We can also convert the slope because it will always have the same sign as the correlation coefficient, but it's unstandardized, and we can kind of get the correlation coefficient from our beta coefficient. One reason why people like to standardize their measures is so that then the beta coefficient is the correlation coefficient in a one parameter model. But last little thing is that the sum of all the residuals in our model end up being 0. And a corollary of that is that the residuals and the x value are uncorrelated, which is really nice. And apparently this line is broken. Cool. But anyway, so let's talk about assumptions of least squared regression. So from your earlier courses, you hopefully remember linear models have two. One is normality of errors, that the errors are normally distributed, and that the same variance of errors holds for all groups, that there's not an unexplained chunk of, like, that all your data come from the same source, is what I'm trying to say here. That is, your variance is nice and even. Cool.